Hello everybody, welcome back. Today we're going to take a look at the problem in Lab 8, which looks at non-linear gradient descent. And for this example, we're going to take a look at data that looks like this. Right? We have almost two different components here. Right? We can see that in our model here, a linear component and a sine component, right? A wave component, something that's oscillating. We can see the linear component illustrated by this line. There's some kind of trend that our data is heading upwards. And the slope of that line, right, whether it's down here, whether it's down here or up like this, is controlled by this theta. Theta 1 is sort of like our slope. And the frequency that our sine wave oscillates with, that is this kind of up and down pattern here, is controlled by this theta 2 here. So this guy is kind of like our frequency. Right? And adjusting this theta 2 would leave us with different results. We might end up with something that has far too high of a frequency, or we might end up with something that has far too low of a frequency. So our goal with this problem is to tune our theta 1 and our theta 2, that is our slope and frequency, in order to closely match the blue data we have here. Right? And we remember gradient descent does this by minimizing the error between my model and my data down here. Right? So just to get started, we first create a function to represent our model, our sine model. Right? We have an input argument of x, which is our attribute here. Right? Could be heights, could be weights, right? Whatever it is, that's our attribute we're looking at. And we have our thetas. Again, our slope and frequency, which we can see here our function expects to be an array of theta 1 and theta 2. And down here, we simply return our model's function. Right? Return theta, so it's giving us theta 1 times x plus the sine of theta 2 times x. Right? Both our linear component and our oscillating sine component. We remember that our model is trying to predict the y-hat values. Right? These values over here is what we want our model to predict. So this function returns y-hat, or our predictions. Returns predictions. Alrighty. Our lab now shows us that we need to create 4 functions. Right? We have a sine MSE, that is our mean squared error, the first derivative, or the partial derivative with respect to theta 1 of our MSE, and the partial derivative of our MSE with respect to theta 2. And here at the very bottom, we have something called the gradient, which we'll talk about once we've derived these first 3. So just to get started, our sine MSE function. We recall the mean squared error, right, our MSE. Our formula is 1 over n times the sum of our actual values here, right, our actual data points. I'll maybe make that blue so it relates to the graph above, and our model's prediction of the y values. Right? The thing that this guy spits out, y-hat. And of course, we square it. Right? Now, a different way to interpret this guy right here, 1 over n times the sum of all of these, is just the mean. Right? The mean, remember way back from our algebra classes, right? We sum up our values and we divide them by the number of values, which is what we're doing here, right? We're summing up all of these distances between the actual data points and the predicted data points that are squared, and dividing it by the number of data points we have. Right? So another way to look at this would be by first getting this y-hat value, right? And we can do that with, well, we already have a function for that, right? So looks like sign model. So I'll say y underscore hat equals, and we'll use this sign model right here, which is green, so I'm going to also choose green for that. Whoops. Sign model. We will pass it our x and our theta, right, which we have as input arguments here, our x and our theta. Right, this gives us our y-hat values, and then we can get our MSE. So I'll have down here a return. Right, this is what we want this function to spit out. np.mean. Right, we want to take the average of something, and we're going to take the average of our y values minus our predicted y values, right, which we called y hat above. Of course, we want to square these guys, squared, and that's it. Right? This function now returns the value of error for some given thetas. Right? So, what can we do with this? Well, if we recall, right, from our kind of gradient descent of what we're trying to do, whoops. If we recall, our gradient descent needs the actual value of whatever function we're trying to minimize. Let's say it's this arbitrary function here. We need the actual value that that function produces. So this value here, which would be our MSE, right? So we have that. That's this guy right here. Our actual y value of the function we're trying to minimize. But we also need the derivative, right? We need to know how this function is changing. Right? And in this case, we have two thetas, so we'll need two derivatives. Right? Again, if I redraw this guy in 3 dimensions here, or at least attempt to, right, say we've got some kind of bowl shape here. That is a poor bowl. We're going to try that again. Right, say we've got some kind of bowl function here. We need the derivative, say our point is here, we need the derivative in this direction, and we need the derivative in this direction. And that is known as a partial derivative. And we do that by taking the derivative with respect to a different variable. Right? So for this guy, dt1, right, this means that we want to take the derivative of our MSE function with respect to theta 1. Right? And down here, we'll do a similar thing, right? The derivative of our MSE function with respect to theta 2 this time. Right? So in this one, we're going to treat theta 1 as the variable we're deriving, and in this one, we're going to treat theta 2 as the variable we're deriving. Right? In this case, theta 1 is just some constant. In this case, theta 2 is just some constant. All right? So let's go ahead and do that. I'll maybe move over here, and we'll first do this analytically so we can write this out as code. So first, dMSE with respect to theta 1. Right? So I'll start, just as a reminder, my MSE function right now is the mean of my y minus y hat values, and another parenthesis here, squared, right? But I'm going to go ahead and replace my y hat with my prediction. So mean of y minus, right, and we remember our y hat is just our sine model up here, y minus theta 1x minus, right, our negative distributes here, minus the sine of theta 2x. And this whole guy here, we'll use brackets like this, is squared. So we want to take the derivative of this with theta 1 as our variable. So the first thing we see is we notice the chain rule is applicable here, right? We've got our squared up here at the top. So, right, we can rewrite this as the derivative of some function of some other function, right, where g of x is the thing inside of the parentheses and f is this entire outer thing. So first, we remember power down to the 1 less power, right? So my 2 comes out here, and we retain the stuff inside of this function, right? So y minus theta 1x minus sine theta 2x, right? And our previous 2 up here goes down to a 1, so we'll just leave it like this. And next, we take the derivative of what was inside of here, right, our g of x, with respect to theta 1. So first, we see this y. There's no theta there. It's just a constant, so that y vanishes, right? So we have nothing for the y. This second term right here, we do have a theta 1, which is the thing we're taking a derivative respective to. So the theta 1 is to the first power. We do power down to the 1 less power, so 0th. 1 comes out here, and we just end up with an x. Right? Now this is where those partial differential equation skills come into play. Right? We see this sign here, and we see a theta 2 in there, but we remember we're not taking the derivative with respect to theta 2. It's with respect to theta 1. So theta 2 is just a constant, which means this entire guy right here is just a constant, which means it drops off, right? So this guy actually doesn't make its way out here. Now you'll notice this right here, right, or more specifically, this right here is the same thing as y hat, right? So we can reduce this down to 2 times y minus y hat times x. And this is the derivative of the MSE, the mean squared error, with respect to theta 1. It is actually what we want this function here to spit out, right? The equation of, we'll write return, and of course we need to get our y hat again, so we might need to compute that first. Y hat, whoops, y hat, and we'll do it the same way we did up above, right? We can just run our sine model with x and theta, I'll abbreviate it, and now we can return what we got down here. 2 times y minus y hat, the thing we got above, times x. Right? This is that derivative. This is the direction theta 1 is heading. Right? So, coming down here, we'll do the exact same process, but this time for the derivative of the MSE with respect to theta 2. And again, just for my own reference, right, I'll write this guy out again here. Mean of, whoops, forgot here, we still had that mean, right? So I'm going to scooch this out, and we'll say mean of this, right? Because we're doing this for multiple x's, so we want to make sure we get the mean. Here, I'll come back over here and continue. So the mean of y minus theta 1x minus sine theta 2x. This whole thing is squared. And again, we'll apply our chain rule. So remember, power down to the 1 less power. So we get 2 times the mean. This time I'll include the mean. Times the mean of our original function, right? So y minus theta 1x minus sine theta 2x. Right? Our original function here times the derivative of this inner function. So times whatever that derivative is. Now here is where it gets a little funky again, right? So y, since we're taking the derivative with respect to theta 2, y is just a constant, so there's no y here, right? In this case, right, previously, we had a theta 1 times x, right? Theta 1 times x. But in this case, theta 1 is not what we're taking the derivative with respect to, right? It's theta 2. So this guy is actually just a constant as well and vanishes. So there's no x or theta 1 here, right? But this guy, this sign right here, right, that has a theta 2 inside of it. So for this one, we do actually need to take the derivative of the negative sine and theta 2, which, if we remember, right, comes out to be the cosine, and I can't forget my negative out here, the cosine of the inside, theta 2x, times the derivative of what's on the inside, right? And if theta 2 is what we're taking the derivative with respect to, right, power down to the 1 less power, so 1 times theta 2 to the 0th power times x is that derivative. Well, that's just 1, and 1 is just 1, so we just end up with an x, right? So times x. And I'll go ahead and close out my mean right here. Now this is the equation we want to implement in our function over here, right? The derivative of the MSE with respect to theta 2. Again, we can compress this a little, right? You remember that this expression right here, if we factor out that minus 1, is the same as, I'll go ahead and just write it right here, it's equal to 2 times the mean of y minus y hat, right? That's what this guy is. Maybe I'll like that, times the negative cosine of theta 2x times x. Alrighty, so now I'll leave it up to you guys to implement this guy, this guy in here. Alright? A minor correction that I'm realizing that I made over here, right? Notice that we had a negative sign, so it resulted in a negative cosine. Up here, I forgot about this negative, right? So this x should actually be times a negative x here. Negative x, right? Because we have that minus sign right here. Alrighty, so this gives you both of our derivatives, right? That is the direction the slope is heading, which we need for that gradient. And down here, in our actual sine MSE gradient, right, this one, we want a single function to just represent the two-directional gradient, that is where theta 1 is going, and where theta 2 is going. Right, so to implement that, we can simply, right, we'll say return, we can simply call, well, first we want to make a numpy array, so I'll do np.array, and we'll construct our array here. We can simply call the above two functions to get our gradient, right? Or our piecewise derivatives, right? Our partial derivatives, excuse me. So sine MSc dt1, sine MSe dt1, of course, passing the correct corresponding values, which are given right here, right? Comma, sine MSe dt2, right? That second derivative. And again, this is just to nicely bundle up our gradient, right? And that should be it for this lab.